Hi, everybody. Today I will be showcasing how RGB technology for doing confidential assets on top of Bitcoin and Lightning Network, private and scalable with a client-side validation, how this technology can be integrated into the wallet software. I assume this presentation will take about less than 1 hour. I have 32 slides with diagrams and explanations, so let's get started. A brief update of what's RGB and other related LNPBP Standards Association projects. What is their status today? We are 1.5 years already of work in progress on RGB and Lightning node implementation. And it started in the mid-2019 with a new iteration. We had a lot of experiments before, and we started from scratch at that point, and we also started this LNPBP Standards Association. Since that time, we have created more than 30 pure Rust libraries and wrote more than 500,000 of lines of Rust code, made more than 100 contributors, like issues, pull requests, and with the tens of thousands of lines of code for Rust Bitcoin ecosystems outside of RGB, meaning for normal Bitcoin stuff and Lightning stuff, because a lot of things that we are developed required advancing existing libraries, existing Bitcoin libraries further. In this process was involved more than 20 contributors. Currently, on what we are aware of, there are at least 2 wallets being actively developed, and at least 1 exchange working on integration of RGB. We also have information of 2 other exchanges considering to join and to start working on integrating RGB. So there is a good traction already, and we are trying to get up to speed for providing these developers with the necessary documentation, APIs, and SDKs, because most of this 1.5 year and most of the code that we've written, it's the core technology, the core RGB technology, it's business logic, validation, and so on and so forth. And APIs are still being actively developed. And before we will have a first wallets and first exchanges working with them, we are not yet sure that we have everything completed, but we are trying to do that as fast as we could. And we know that there are at least 2 other known projects from outside of the companies who are in the other part of LNPBP association. They are also looking into integrating RGB and starting playing with it. So our current status is that we have released last week version 0.3, which main update for this version was the fact that we rebased everything on top of new Rust Bitcoin release and new mini-script release, which required very light-scale refactoring, and we used this refactoring to audit and review the code once again and improve the library structure. I've been doing an in-depth coverage of this refactoring and release on the last call, so I wouldn't pay a lot of attention to this today. This week we've got branch 0.4 into development of all main libraries, meaning RGB libraries used by Lightning node and so forth. The milestones with this branch is that we would like to complete SDKs and get the first wallet or wallets running with the RGB. We are aiming to have a full Lightning Network compatibility, meaning that we would be able to create channels with other Lightning node implementations. Of course, they will be operating in Bitcoins only, because for other Lightning nodes, they don't support RGB. But we think that we are really near toward this goal, and we will be able to complete it soon. We have a project board in the LNPBP GitHub organization called LNP node, where we have all the tasks that are left in order to get to this very important milestone for LNP node. Also, this version will support universal invoices and required partially signed Bitcoin transaction extensions. which we will be discussing today. These all parts are very important for the wallet integration and workflows with the transfers between the users. So this version will ship these parts of the functionality together with the rest of the things that I just mentioned. So I think we can start with reviewing the way how the wallet can work with the RGB SDK. And the presentation will be made in form of sequence, UML sequence diagrams, where you will clearly see the workflow between different components. Each component is a vertical column. You have the name of the component on the top of the column, and the arrows shows which way the requests and information is flows. So it's quite simple to understand. It doesn't require a lot of technical understanding, and it's a very good guideline. I have originally developed that for myself to make sure that I'm not forgetting anything when I'm integrating into RGB with RGB. So these main columns, I will start with the overview of the actors participating in these workflows. The first actor on the left side always is the actual user. So it's not the program code, it's nothing like that. It's just the column used to denote user actions and interactions when user need to do something like copy paste invoice or take a decision. The next three columns is wallet related columns. They are done by wallet developers. So it's everything that happens there is the part of the wallet developer and its internal wallet business logic. Why three columns? Because we have a user interface or view, we have a controller or business logic, and we have a storage or model that is responsible for persistence of the data. And the most of the software, modern software, follows this three-type separation of concern, three-tier separation of concern, and that I think will simplify wallet developers to simplify the understanding where a particular part of the functionality should be developed. For instance, everything that is related to wallet storage, it has to be carefully managed in terms of backups and making sure that the data are kept persistent. The very important, which is 1, 2, 3, 4, 5, the fifth column is actually the hardware security modules or hardware wallets. It's not necessarily hardware wallets. It's rather that part of the wallet which is responsible for signatures. So all these three wallet columns before that, these are read-only wallet part of the wallet. So it doesn't have access to any private keys. It operates with public keys only. And whenever we need to sign transaction, it is done with a hardware security module. Many wallets do not work with a hardware security module. They have a signature process inside themselves. So basically, in this case, it will be just another component of the mobile or desktop wallet. However, because we would like to make sure that technology will work with all the existing ecosystem, that's why we split it into separate column. So you can make sure that this works with external devices, external hardware storage devices. And the next column is actually RGB SDK or RGB node, depending on the type of integration you choose. So you can work with the remote node on the server side, or you can embed the node into your mobile application and work with it through the SDK using language bindings, or you can develop your own code in Rust code, and then you don't need RGB SDK. You can directly talk to the RGB node. Whatever mode you will choose, you will still have the same API, just wrapped into different language wrappers. And this API is, in fact, presented within this column. So this is the only part that is done by RGB itself. So it's a black box. You send the request there, and you get a response. And we are not going into internals of how RGB work here. And the last actor is actually a network. Well, it's a broad name. It's networks, in fact. So depending on the situation, it could be a Bitcoin Core server or Bitcoin P2P network, Electrum server, or it could be a Lightning network, or even in the future when we will complete an RGB infrastructure services like Bifrost can be RGB related part of the Lightning network. So in each case, I will be specifically saying which network we are talking to, but just to reduce the number of columns, I put them all into a single columns. Also, there will be not a lot of requests that will be going through the network. So once again, the wallet columns are developed by the wallet devs. So this will be part of the your work. You can make these things work differently. For instance, you can change the way you would like to process the information. So here is shown the recommendations and best practices which should prevent from the most pitfalls and security issues. The hardware security module is either done by the wallet developers, if they would like to keep the private keys within the wallet using software components, or by hardware developers. As LNPBP Standards Association, we will be working. We already started talking to most famous developers of the hardware wallet. And we already started finding out what it takes and what is required in order to create extensions and applications that can be shipped with a ledger, with Trezor. So people will be able to spend RGB assets, sign transactions, and do all of that stuff. And many parts of the discussion today, like extension to partially signed Bitcoin transaction, actually came from these discussions and from these investigations. So we tried to fit the SDK into this. And LNPBP Association will be, in the future, once we will complete with the other priorities, will be probably developing this application for the most common third-party hardware wallets. Also, the LNPBP Association is a non-profit company. It's not a company, it's non-profit association. However, I also have a company which is called Pandora Core. And if any of the wallet developers who needs to understand, to get the support, or to get the pieces of the workflows that I will be presenting today as ready-to-go components, they can talk to us and we can find how we can help them with the consulting of white label solutions. Okay, so let's start. The first task when you work with a wallet is creating an invoice normally. In Bitcoin world, you don't have an invoice. In on-chain world, you have an address, so still you have to find an address and share it. And address is a bad practice, which leads to the reuse of public keys, leak of confidential information. So with the Lightning Network, we have a more developed concept of invoice, and we inherit this invoice and take it further with RGB, such that these invoices will be applicable not only for RGB, but also for even on-chain Bitcoin transactions, preventing from the bad practice of public key reuse and address reuse. But I will be talking about the invoices a bit later. What I will start with is the generic workflow, how you can create the wallet. So, of course, it's always a user activity. So user asks wallet for an invoice. Wallet user interface brings this task to the business logic, and business logic talks to the RGB SDK or RGB node, calling a single function called invoice. This function will have different parameters of the invoice taken from the user interface. And the return of this function is actually a binary invoice data and a blending secret. So in case of RGB, it's very important to understand that when we create an invoice, we create actually not an invoice, but two parts of the invoice. The invoice is the public part, the part that can be shared with the external world without any leak of confidentiality, or almost no leak on the confidentiality, depending on the data that you will select to include into the invoice. In many cases, invoice will have different formats, but if you will use a specific format of invoice when you will be selecting existing Bitcoin transaction output from the Bitcoin transaction, unspent Bitcoin transaction outputs that you own. In that case, you would like to hide the fact that you own this transaction output. So when you will be creating invoice based on UTXO, you will be blending the information about the actual UTXO with some secret data. And this secret data are called here and further in the presentation blending factor or blending secret. Actually, better to use blending secret because blending factor as a term has other use in the cryptography. So blending secret. And this blending secret is a 46-bit integer, which must not be shared with the external world. And you get from the RGB SDK these two things, the invoice and the blending secret. And the blending secret you need to store in your wallet. And this is the task of the wallet, to store this safely. And if you will lose it, you wouldn't be able to receive and spend the assets. That would be a very pity fact. So this is very critical, mission critical information. And this information is not recoverable. So this is the only unrecoverable information on these slides. The rest of the information can be recovered from the data that are kept by RGB node. Here, this secret can't be recovered. Why do we split the secret from RGB node? Why RGB node do not stores the secret? There are two main reasons. The first reason is that RGB node in fact, RGB node will be working with the large pieces of data. And quite soon there will be wallets that will be running custodial RGB node on their servers. So I'm quite sure that we will witness these custodial RGB nodes, and the node wouldn't be owned by the user. So this would be a protection from this custodial solution. So this small secret, a very small number, will be kept by the wallet. So even in custodial wallets, you will still maintain the privacy. The second part is more important reason, is that when you do a wallet, it might be that you will like to share the information between different wallets. For instance, you have two mobile devices like iPad and iOS, or you have iPhone and Android phone, or desktop and the phone, and you run the wallet on two devices. And these two devices, they have different RGB nodes. And you create invoice on one device, but you receive the payment on the other device, and you would like to spend that funds from the other device as well. And in this case, you wouldn't be able to do that if the secret was kept in the RGB node. If you keep it inside your wallet, you will be able to set up the infrastructure where mobile and desktop wallet developed by you will be sharing this secret via other channel. So here is how the invoice is created. Once it's created, it is presented to the user via user interface. And the way the invoice is presented is back32 string. So if you will be using Wallet SDK, you will get the invoice actually as a backstream already. If you will be using lower level API, you will be getting invoice as a binary structure with ability to convert it into backstream later. And that is actually, this backstream, of course, can be presented as well as in form of QR code as well. So user can paste it, can scan the QR code. It's pretty much the same as it works with the Lightning invoices. So from here, I need to spend some time discussing the universal invoices and back32 encoding that is used across the RGB library. So universal invoices is a work in progress. We will be writing a standard definition of the invoices. We reserved number 38 for it. And they are actually, we had a separate call dedicated to the universal invoices. It was several weeks ago, and I asked all of you who are interested in this topic to watch it. It was in-depth presentation and discussion of the matter. Briefly, these invoices are back32 encoded strings that support both on-chain and Lightning payments They support multiple asset formats, so you can work with the native assets like Bitcoin, or you can use RGB or confidential assets, and I assume potentially, from what I know, it can be extended to other types of assets if required. They allow you doing stuff like aggregating payments for coin joins, aggregating transactions. They allow you paying to multiple receivers. They allow you to supply very complex forms of interaction and information. This is all very extendable. How it works, again, I would like to offer to watch to the demonstration, because it's not possible to cover all that within the talk today. Since that presentation and discussion, we had an ongoing work, and we got a feedback. And basing on this work and feedback, we have few updates which were not covered in that presentation, so I will cover them right now. We are getting rid of network ID field, because set ID, it uniquely identifies the network as well. We are getting rid of, we had a field with information who can pay the invoice. We're getting rid of it because of the confidentiality issues, and because it will lead to creation of whitelists and that stuff that we don't want to have. Also, if you will if you want to receive a payment from few payers, you will just share this invoice with only those payers. If you'd like to receive the payment from a broader audience, well, you will have to provide a many payers in this field, which will create a huge invoice, which wouldn't be usable. So basically, there is no reason of having this field at all. We found a way how you can basically use the same invoice format without any modifications to pay to multiple beneficiaries. So you can split the single payment across multiple receivers. And for this option, we will be using partially signed Bitcoin variant of the invoice. So for the invoice standard that we were discussing, we had 4 ways of specifying beneficiary. Actually 5 ways. The first way is just normal Bitcoin address. So if you would like to use them, you still have the option to use normal Bitcoin addresses. There is also a miniscript descriptor format. So you can define your wallet with a hierarchical derivation information in a miniscript descriptor format. You can also use a partially signed Bitcoin transaction, and this case is very important for stuff if you will be doing coin joins, or you would like to aggregate a couple of invoices into a single payment, or you would like to, or you plan to do it with a complex multi-sig setup, or like here, you can use the same PSBT structure to structure a payment to multiple beneficiaries. So basically, as a merchant, you create an invoice and you create a template of partially signed Bitcoin transaction, which is part of the invoice. And in this template, you create outputs for other receivers, other beneficiaries, specifying right inside the output how much they should receive of the funds. So you can basically structure it this way. The first format is specific for RGB, and it allows you to pay to UTXO with this blending factor, blending secret. So this will be the only option of invoice when the blending secret will be produced and used. And the fifth way is actually paying to the Lightning node and Lightning node address or Lightning node destination. And with that option, you will also have ability to create invoices inviting to open channels with specific node and so on and so forth. So that's what was discussed in that presentation of the invoices. I wouldn't go further into the details. The next update that we had since that time is that we found a way how we can reuse a single field for that is used today for HTLCs. When you do a Lightning invoice, you have a specific information about hashed secret. required for the payment. However, in the future, the Lightning Network plans to move to the other format, PTLCs, and we found a way that actually the Schnorr keys, which will be used for PTLCs, they have the same dimension as HTLC, so you can store them as well in the same invoice format and mark that with a special feature flag, which is already included as a part of the invoice. We also propose that the details field may be used to specify connectivity with merchant or some interactive payment protocol when, for instance, you may need to get a slip signed by the merchant about the payment. And TLV extensions that are part of the invoice format, they also may be used to create invoices not just for RGB fungible assets, but also for non-fungible assets and other forms of RGB smart contracts. So this is a more broader format than just invoice for fungible assets. So I invite you to join the discussion. We have the initial implementation created, mainly finalized, and it will become a part of version 0.4. And the next question related to invoices is BAC32 encodings, how it's used throughout the RGB and LNP ecosystem and invoicing protocol. There will be a dedicated standard to that. And we have two use cases. The first use case, which we already started using initially, is the use case more broad than RGB itself or invoicing protocol itself. The core idea is very simple. BAC32 is quite useful because of two things. The first thing, it's very simple to check the integrity of the string. It provides a checksum within it. It ends the BAC32 string. And when you need to compare two large pieces of data, for instance, in debug logging or anywhere, you don't need to compare, for instance, if you print a bytecode or if you print a hex representation, you will need to compare each character, which can take a long time and you can easily miss something. With BAC32, you need to compare just 4 or 6 characters, I don't remember exactly, and that's all. And the second, it's very easy to copy and paste it between software, between devices, present it in QR code, and that makes BAC very useful outside of Bitcoin world and outside of RGB world. So we have created a small module in the library that allows you to encode arbitrary binary data as a BAC string, and this data will have a prefix data, which is very simple. So we don't know anything about the format of those data, but if you need to share some binary data between the application or display them in the logs, you can use this data representation. Another variant of this data representation is compressed representation. So because some binary data can be very large, you can also have a BAC representation that has embedded compression. And also it's being developed and it's already working, so you can compress them. And in that case, you will have Z1 prefix. And the last thing are the identifiers, which are created from hashes. We require that these hashes should be according to taproot rules. These hashes can come from outside of Bitcoin world, and these hashes will be prefixed with ID tag, specifying that this is a hash of something. In RGB, we already have a set of BAC encodings and prefixes, which will be used for sharing for asset information. So asset has unique asset ID, which we call contract ID. It is a hash of the genesis of the asset, and it will be prefixed with RGB1. So whenever you need to specify in which asset you would like to be paid, this is unique identifier. Aside from the ticker can be reused. There could be a scam coming with the ticker. The BAC string with RGB1 uniquely identify a set, and you can easily recheck it with the check code, with the check bytes of BAC string as you do for Bitcoin BAC addresses. Genesis 1 are Genesis data, and this is an exported format of Genesis. Whenever you create an asset today, you will have to share this string with other wallets who would like to receive it, because this piece of information will contain everything about the asset. So wallet, if it need to receive some payment in some asset, it will also need to get the Genesis 1 back string. You can generate it with an export function of the RGB SDK. And later on, of course, we will plan to use Bifrost infrastructure to distribute information across the network about newly issued assets. Or wallet developers, they are free to create their vendor-specific servers that will just propagate the assets across all the wallet instances. So users will have some set of supported assets and got from the wallet developer server. And I recommend to store this asset information not in a binary form, but in the form of backstrings as well, because asset genesis is quite small piece of data, and it will not require you to integrate the RGB SDK or any RGB libraries to support just storing that information in the database. And probably, potentially, we will create a native language-specific applications to libraries to parse this backstring, so you wouldn't need to integrate a heavy-duty Rust stuff coming with RGB. The next backstring is UTXO B1, which is the representation of the blended UTXO that is used inside the invoices. The other one is, the other two are actually related to schema. The schema is a part of RGB protocol that defines the format of the contract. For instance, it could be a fungible asset, they have one schema, non-fungible tokens the other. If you will have an identity standard, it will have another schema. And each of the schema, they have their own identifier, which start with SCH prefix, and the binary representation encoded in back format, which starts with a schema 1. And the one that I missed here is the proposal to use I prefix for the back32 encoding of the invoice data. And this will be non-RGB specific. It may be used more broader than the RGB invoices. As I said, it's suitable for Bitcoin payments as well. The materials related to the back32 encodings are here. There is a discussion link and initial implementation for the common part of encodings and RGB specific part with these links. So that's all for the invoice overview and back32. And we are moving to the second task, which is actually how we can pay an invoice. And before that, I think we need to spend a few moments to check that maybe somebody have some comments or questions regarding the part that we already covered. I don't see the chat. Maybe there are some questions in the chat.
There are no questions in the chat just yet. And guys, I wanted to ask you, if you don't understand something, or something was very fast, was described very fast, feel free to ask right away, because it's better to know if something is not digestible right now than to just skip it and then have some troubles with understanding it. So yeah, if you have any questions, just ask.
Okay, let's dive into paying the invoice. The process starts with the user who got this back32 string of the invoice. It pastes it into user interface. It calls the pay invoice method of the wallet controller, which actually will do the whole heavy-duty job. The first step of that job is that actually the wallet has to parse the invoice, and it is done using RGB SDK. There will be a specific dedicated method to parse the invoice. It's not there yet because we don't have the support for that new invoice format. The invoice format that was used before the version 0.4 was much easier URL, which we don't need to parse. Here, there will be a method that will return the parsed version of the invoice data with a JSON representation. And as I said, in the future, we plan to have native libraries in different languages supporting this parsing because it's not very complicated. Once you have the invoice details, of course, you need to present that to a user, and user need to make a decision. I wasn't putting that into the chart because otherwise it will become enormously large. But before presenting user, you will also need to get to know that you actually can pay this invoice. So you also need to ask RGB SDK on the update of the assets. So you have an asset ID from the invoice. You know in which asset you need to pay, and you ask RGB SDK to give you a list of the outputs and how much of that asset do you have. And for that, you use asset allocations API call from RGB SDK. It's already there. And in return, you receive the list of Bitcoin, unspent Bitcoin transaction outputs. Sorry, actually, RGB SDK will return you the list of all Bitcoin transaction outputs with the amounts. And it will be up to the wallet to make sure which of these Bitcoin transaction outputs are unspent and which of them need to be spent. So you will be actually checking the out points that they can be spent, and you will do the coin selection. And basing on these two procedures, the wallet shall prepare a partially signed Bitcoin transaction, spending the outputs with the assets which were selected by the coin selection and which are not spent yet. When you have a PSBT created from that, this PSBT contains no RGB information. You just spent Bitcoin transaction outputs to some new addresses. Mostly, in most cases, if you're paying RGB invoice, these Bitcoins will go back to the address that you own. So you will create a single change address and a number of input addresses required to spend the RGB assets. You ship this PSBT together with the invoice and the information on additional changes in RGB assets, not Bitcoin change, but RGB asset change, to the transfer method of RGB SDK. And what RGB SDK does with it, it actually does two things. First, it updates PSBT with all information that is needed to spend these RGB assets correctly. So it should allocate the change according to the change information you provided. And actually there is an issue reported a few days ago that there are potentially some bug in this process, which we will be fixing this week. And it will also tweak it will put the commitment to the spending operation into one of the outputs, or if you spend the multiple assets into several outputs with all the deterministic Bitcoin commitments that we have. And the SDK, as a result of this process, will return two pieces of information back to your wallet. The first piece of information is actually updated partially signed Bitcoin transaction. And the second piece of information called consignment. Consignment is actually a binary data. You don't need to know anything about them from the wallet developer perspective. It's just a blob of data which must be shared with the receiver of the payment. These are client validated data without which the receiver wouldn't know he received the payment, and he wouldn't be able to spend those assets. So without the consignment, the transfer would not happen. It is important that to understand that the commitment to the payment, the actual payment, happens at the moment when you publish the Bitcoin transaction, not at the moment when you create consignment, not at the moment where you share consignment, but at the moment when the transaction got mined and or got signed inside the Lightning channel as a new state of the channel. And this means that actually we will be covering the publication of the transaction later. Right now, the actual payment haven't happened. And first of all, if you will share the consignment and wouldn't publish the transaction, the only thing that you lose is a part of the confidential information, but you wouldn't lose the asset. The second thing is that if you publish the transaction, but would keep the consignment and wouldn't send to receiver, you actually lose the funds anyway, because you committed to the payment with the transaction, and it allocates the RGB assets to the outputs owned by the receiver, and consignment make no use for you. But if the receiver wouldn't have this consignment data, he wouldn't be able to use the assets as well. So actually assets are lost until the receiver will get this consignment. This procedure is already implemented, as was shown as a part of the demo on the previous version of our RGB node, and it was happening from the command line interface. When you were calling the transfer method, you was shipping this transfer method with a PSBT file, and it created another PSBT file and a consignment file. The next block is actually wallet's job on preparing partially signed Bitcoin transaction, because it's unsigned. It only has the RGB specific data, but it doesn't have a signatures. And what a wallet has to do is very specific process, specific to RGB, which is important to understand. What is it? The fact that you create a commitment for each RGB transfer inside the Bitcoin transaction output means that whenever you will try to spend that Bitcoin transaction output, you wouldn't be able to produce a valid signature because the key was tweaked. And these commitments, they're not one-to-one related to the RGB assets. So frequently, there will be situations when normal Bitcoin outputs having nothing to do with RGB assets have a tweaked public key. And these outputs can't be spent without providing this information. So that's where the blending, that's where the tweaks are coming into play. And later I will be explaining that you will always save the tweaks that are applied to public keys in partially signed Bitcoin transaction. And I will be showing where in the partially signed Bitcoin transaction this information goes into. Your wallet, first of all, has to extract this information and store it for the later use. Store it inside itself or potentially on hardware security module, but better inside the wallet. And the second, it must extract the tweaks that are related to the inputs of the transaction. So you do two things. You create new outputs and there are new tweaks. You save this information. And if any of inputs spans the output that were tweaked previously, you need to retrieve that information. And you make this information, you extract this information and make this information part of the PSBT. So you get one information out of PSBT and you put another information into the PSBT. That is called PSBT processing. Once you've done that, you send partially signed Bitcoin transaction for a signing module, hardware or software, and hardware signing module checks the PSBT data and it signs it. And there is another very important question, because it must be able to sign the tweaked keys. It must be able to extract the information from partially signed Bitcoin transaction on the tweaks, apply them, and it also must present user, if it is a hardware security module, with interface information that actually this transaction contains a tweak and parse the data which RGB assets were are paid and spent and to which receiver. So this is done. This is already was discussed with the hardware developers. If you do that inside software in your wallet, it's not a big problem at all because you use the same wallet logic to do that. It can be done also with a hardware developer, hardware modules, and I will be showing how this can work with the current existing PSBT format. The result of this operation is actually you get back a signed version of partial Bitcoin transaction. So all fields are signed and you are able to publish it to the Bitcoin network. There is a special, not yet. The next step, once you have a signed Bitcoin transaction, is to share the consignment. And this sharing can be done in 3 ways. The first way is that you can do it manually. You can display it to the user or provide it to the user as a file binary file or backed 32 string. We have a special encoding for that, and the user copies this backed string or binary file and send to the receiver where other channels. For instance, he can provide, he can paste the back string into email message or into a telegram, or do whatever he likes, or embed binary file into the mail message. This is least convenient way, but this way allows you to bootstrap the RGB payments without creating any infrastructure. The better way is actually that the wallet developers will create some vendor-specific way when it will be uploaded to a wallet server, and the other wallet, if the other user uses the same wallet from the same provider, he will be able to get the consignment by his ID, by ID of the consignment. So that is the second way. And the third way is actually when we will have a Bifrost infrastructure up and running. That would be one of the main goals of this Bifrost infrastructure. You will be encrypting the consignment with a key, the receiver key, which you will get from the invoice, and you will upload it to Bifrost server. And the user, from the receiver of the payment, he will contact the Bifrost infrastructure as well from his own side. He can provide the information about desired Bifrost server as a part of the invoice once again. So he will be able to contact that Bifrost server and get the consignment downloaded to his wallet and get the payment by this way. So this is how the consignment sharing is happening. The next thing that there are very important case where you have a multi-sig setup, and the signatures must be produced by different users or different devices. This is also, we have also this covered. And for this case, I wouldn't be going into details into this case, how this works. There are charts explaining that. And today we just don't have a time. If any of you are developing multi-sig wallet, please contact and we will dig into this part of the story. But let's assume that PSBT is fully signed. In that case, we extract the transaction, we publish transaction to the network, and we show OK to the user that the actual payment is happened. So first we shared the consignment. Second, we published the transaction. And variant for multi-sig wallet, it involves many more steps. But once again, if you are interested, let's have a separate call or presentation on this topic. So, regarding this part, regarding the payment, we need to cover a few topics regarding how we use the Bitcoin, partially signed Bitcoin transaction structure to put the RGB specific data. So what are these data? Let's start with the Bitcoin transaction structure, partially signed Bitcoin transaction structure. What's it all about? Well, actually, the idea of Bitcoin, partially signed Bitcoin transactions, PSBTs, I will call them PSBT, is the need to run multi-sig wallets and to use hardware security devices to sign the transaction in a standard compliant way. The Bitcoin transaction itself do not have a lot of information. It is optimized to reduce the space it uses in the blockchain. That's why it skips all unnecessary details that can be reconstructed from the blockchain. But when device signs the transaction, it do not have access to the Bitcoin blockchain. You can't retrieve this information. And this information is, for instance, amounts which are spent. So you don't know, you just see the outputs, but you don't know how many Bitcoins are there on those outputs. And of course, you don't know how many RGB assets are there. Because of that, you are not able to compute the fee you are paying inside this transaction from the pure Bitcoin transaction. The next thing is that when you create outputs, you use a hash of public key or hash of script, and you can't understand how this output can be spent. You won't be able to predict that whether this output can be spent with the keys that you own or can't be spent, especially if this output is a complex script output. It may use some hash lock secrets, or it may use multi-sigs from other users. And without this information, you can check when you create the signature that you are not doing something wrong. And there was a lot of hacks around that. And that's why the partially signed Bitcoin transaction format was created. And what it does, it attaches a key value maps into three places. First, it attaches one global key value map to the transaction itself. And this key value map provides details on such things as a list of extended public keys, derivation paths used, hashes for hash secrets, and so on and so forth. The information that is common for the transaction. The second type of key value maps attached to the transaction are attached to inputs, one per each input. And this information provides you a previous transaction that you spent. And out of that transaction, you would be able to retrieve information on the amounts. You would be able to check that the signature you create would be able to spend that output. And you also use these maps to put the newly created signatures. And the third thing is actually a key value map attached to each of the outputs. And here you put the full script source, and you put the key derivation information that must be used in the future to create a payment from this specific output, to spend that specific output. So three maps. What we do with RGB, how we can add the RGB information to PSBT. Let's say that we have a transaction that spans two assets, two RGB assets, three inputs, two of them spending assets, one asset, 20 USDTs, for instance, and the other some other asset, tick, let's name it tick, whatever. What should we do? First of all, we should put information about public key tweaks into the input, previous public key tweaks. So if any of these inputs are spending output that had a tweaked key, that had an RGB commitment, we need to specify that inside PSBT. So the wallet, the hardware wallet or module of the software that creates a signature would be able to extract that data, apply them to the secret keys, and create a valid signature. Here you see that the tweaks are applied not to the transactions that contain assets. It has no relation to the RGB assets being transferred. It is related to the previous transactions. So inputs that do not have RGB asset may contain tweak, or there might be a situation when input contains both asset and the tweak itself. So this is the first piece. And this piece is added by the wallet and taken by the hardware security module. The second part that we need to add here is actually information about the new tweaks that should go into the transaction outputs. And this information called anchor in RGB, it's a binary data which are computed in such a way that they result in a value that is added to the public key, and this value is actual commitment to the transfer that you're accomplishing. Why you need that? You need this. You need that for hardware security module, so it would be able to see that you are not just spending Bitcoins. You're creating a transaction that's additionally to Bitcoins spends something else. And you need this data to be kept for the future use. So whenever you will be spending this output, you will use this information to embed the tweak into partially signed Bitcoin transaction, into the input of it. However, just anchor is not enough for the hardware module to understand how many assets, which assets are spent. It's just a commitment, it's just a hash of the state transitions. That's why the third component that we are attaching is actually state transitions that contain the full information about the assets being spent. And these state transitions are attached to the global map because they apply to multiple inputs and multiple outputs. And in this case, if we transfer two assets, there will be two state transitions. So a state transition per transfer. And with this information, what we can check, or hardware security module can check, is actually it can check that assets are spent with a proper commitment. And this prevents hacks when some middleware will modify the data such that neither you will lose your assets and receiver would not receive them. You actually can have a malware that will be creating a commitments that actually invalid, and you lose your RGB assets. With this information, the hardware module can check against that. It also can check that we are not embedding any other tweak, because other form of malware can create additional state transition, and like you spend 10 USD tethers, and it embeds another transition into the same transaction, into the same commitment, and spending, for instance, all the shares that you have at the same time. And you don't know about that, and the hardware security module do not know about that. With this information, it is possible to validate that part of the information. It allows you to verify how much of the asset you transfer, and it also allows you to keep the information about the tweaks that are being applied. It doesn't provide you, though, a perfect security. There's few things that can be reconstructed by a hardware module from out of this information, and they are that if you have other assets assigned to the same outputs and they are not part of the state transition, you will lose them. But this can be efficiently controlled at the level of the wallet, and it can't be modified by malware, because it's removal of the information, not additional the information. And if you will do the transfer, you will see that you're sending, for instance, 2 assets, and the wallet asks you to displace information about a single asset only. So you can retrieve that fact and see that. The second is that it just can't be checked automatically. The second thing is that the wallet can't make sure that the amounts of assets spent are real. So the transitions that it was supplied with are in fact real state transition, not faked one. So, but again, it's up to a user to make sure that he knows how much of the asset he will have on specific outputs he spends. The wallet, the software part of the wallet, should provide him with this information, and he must check that all of the assets spent are allocated to the new outputs with the hardware module. And it is not able to check that the spending itself is valid in terms that the assets are allocated to correct outputs, like you're paying to the real destination. That can be done again only through the user interface of the wallet, and in the same way, exactly in the same way like it's done with the Bitcoin today. So you see, that's very complicated part of the story, and this is very important because while we were able to bootstrap RGB payments with a very simple things, with a one way of paying using, for instance, existing UTXOs, and without doing anything with PSBTs and multisigs, we will quickly run into a lot of hacks, and we will get into trouble. That's why we spent a lot of effort making sure that the design of RGB protocol and design of everything is suitable for work with hardware security modules, with the multi-signature options, with the Lightning Network channels, with everything around the ecosystem. And we actually there where we sure that it all is compatible. Of course, we need more review, including security analysis, that we didn't miss anything here. But fortunately, we are finally at the point where we have APIs and business logic covering all of those cases. And no matter how complex wallet you are trying to develop, you will have the full, you will have the ability to implement all of your business logic here. The action points regarding the PSBT is actually we plan to, when the RGB will be released and we will have more time, to propose a BIP PR for PSBT BIP, making these tweaks apply to the inputs part of the standard, because this will allow for more more hardware wallets to support this. And I briefly discussed that with Andrew Palstra. They're using the same procedure with the Liquid. So this is not very RGB specific. It is used in other cases. And there may be a benefit from such standard. The second part is that some parts of the stuff that I described with the PSBT is already in RGB core library and RGB node, but some of them are not there yet, and we need to finalize that implementation. The current implementation is more than enough for starting a software-based wallet, but it's not enough to work with the hardware devices. So that part will be added to the core library with the next version. And we need to work in the future with the hardware wallet developers to implement software that will enable RGB payments with their devices. So that's all for creating a payment. And the final part is receiving the payment. Once again, I will ask about the questions and comments.
And we have spent 1 hour, so the recording will stop right now. So give me.
It will have another few. Oh yeah, yeah, correct.
Yep.
Let's break it.
Yep.